Hello everyone, my name is Nirvika Rajendra and this is my final Capstone project presentation for Data 606. My project is Student Startup Success Analysis, which is supervised by Chawangi Wang. And in this video, I'll walk through my process, the data, the models I have built, and then the key insights I have discovered. So here is the outline of my presentation. I'll start with a brief introduction and background to set the context. Then I'll walk through the key research questions that guided this project. After that, I'll provide an overview of the dataset followed by a complete data preparation pipeline. Next, I'll present the exploratory data analysis and the insights from the visualization. From there, I'll move into the model training process, compare result, and then explain the model performance. I'll also demonstrate the Streamlit dashboard that I have built for real-time prediction at the end of the video. And finally, I'll close with key takeaways and the future enhancement plan for this project. Startups, especially student-led ventures, are becoming an increasingly important part of today's innovation landscape. However, only a very small amount of these startups are successful. My goal in this project was to use data analytics and machine learning to understand which factors influence the startup success and whether success can be predicted accurately or not. So thereby it enabled institution to improve mentorship, funding allocation, and other strategies using data-driven insights. Student startup contribute to innovation and economic growth, but mostly struggle to scale or survive. So, analyzing historical startup data help identify which characteristic matters the most, such as funding, technology maturity, and team attributes. These insights can support incubators, universities, and then student entrepreneurs in making a better decision. My analysis is guided by five main research questions. So, first is which factors best predict student startup success? How does team size and experience affect the outcomes? And what role do innovation and technology maturity play? How impactful are mentorship and incubation program? Finally, can machine learning model accurately classify startup success? Coming to the data overview, the dataset contains around 2000 student startups projects, and it has over 16 features within the time period of 2019 to 2023. And each row represents a single startup. And also the dataset come from Kaggle, which is focused on student startup success. So this is the data dictionary, which has key variables in the dataset that includes team characteristics, innovation level, funding, institution support, and the target variable is success label. Basically, this table summarizes key features and their definitions and the type of information each variable represents. So this ensures transparency and helps in understanding how the model interprets each attributes. So this is a complete data preparation pipeline I have used in my project. There are six main stages. First is data collection. I began by collecting the dataset that includes key information about student startup, such as funding details, their innovation scores, the mentorship they have received, the business readiness, etc. So this gave me a strong foundation for analysis. Second step is to clean and pre-process the data. So I cleaned and prepared the data by handling missing values, fixing the inconsistency, and converting the data types. I normalized the features wherever it was required. So by doing this, it ensures that the dataset is accurate and usable for modeling. The third step is feature engineering. After pre-processing, I created engineered features to capture deeper patterns in the data. So this includes efficiency ratios. It combined mentorship or incubation indicators and then funding impact measures. So these new features help the model understand the relationship that were not obvious in the raw data. Next is I performed EDA to analyze distribution, identify trends, and visually compare successful versus unsuccessful startups. So this step helped uncover which features have strong influence, and then it guided the model design. Fifth step was model training and evaluation. So based on the insights from EDA, I trained machine learning models, specifically logistic regression and random forest. I evaluated their performance using metrics like accuracy, confusion metrics, and ROC AOC to understand how well each model predicts the startup success. Finally, the last step was model selection and deployment. I selected the best performing model, that was logistic regression, since it provided the highest accuracy and interpretability. I then deployed it through a Streamlit dashboard, which allows the users to input startup attributes and receive real time success predictions. So let's dive into EDA plots. The first plot highlights the distribution of startup success. So the data set has a fairly balanced distribution of outcomes. Around like 42% were successful and 58% were unsuccessful. As you can see in the second plot, all institution types contributed both success and then failures, with non-technical and public institution having the most projects. So here are a few more plots. Funding amount was a startup success, and then the innovation score was a startup success. As we can observe from the plots that successful startups generally have more funding and also higher innovation score, showing both the resources and then creativity help them succeed. So looking at these plots, that is a business model score was a startup success, and then success or failure distribution by a project domain. We can see that higher business model score tend to succeed, showing that the clear planning and a viable model really matters. And then the second plot sees that the success rate are similar across all the sectors. So the type of project domain alone doesn't strongly predict the outcomes. So this is a heat map which shows the funding has the highest correlation with startup with around zero point 0.4, followed by mentorship support, which is 0.37, and then the innovation scores and other factors. So this highlight that financial resources, guidance, and innovations are the key drivers for successful startup projects. And this is a heat map of engineered features. The innovation support index has the highest correlation, which is 0.61, followed with the total support, which is 0.52, and then the innovation funding interaction, which is 0.51. So next is model training and selection. I have trained two models, logistic regression and random forest, using both original features and then a combination of original plus engineered features. So the goal was to see whether engineered features improved prediction accuracy. The first is logistic regression, and it really performed well. As we can see that the original features alone, the model achieved 97% accuracy and ROC-AOC of 0.99. Interestingly, adding engineered features slightly reduced performance, meaning that the original features itself were strong predictors. So I then plot a graph for top 10 predictors of startup success for logistic regression. We can see that well-funded, innovative startup with mentorship, incubation, and then mature technologies are more likely to succeed. So here is the confusion matrix summary. The model correctly identified more successful and unsuccessful startup with very few false prediction. So as we can see that the true negatives were 242, means that 242 startups were correctly predicted as not successful, and false positive, two startups were predicted as successful but actually which was failed, and false negative, which was 10. So 10 startups were predicted as failed but actually they were succeeded, and these are the two positives, which was 166, and it means that 166 startups were correctly predicted as successful. So next model was random forest. So I trained the model using both original and engineered features, and then I also hypertuned the parameters and compare all the three scenarios. And we can observe that the random forest with original feature set has the highest accuracy of 91%. So adding engineered features does not improve random forest accuracy. As we can see, it has dropped to 88%, and even after hypertuning the parameters. So we can say that random forest is robust but slightly less interpretable and low performing than logistic regression. For the random forest model, the confusion matrix shows that it correctly classified most startup success with very few errors. So this is a true negatives, which says that 237 startups were correctly predicted as not successful, and about 7 startups were predicted as successful but actually failed. And this is a false negative of 29 startups which were predicted as failed but were actually succeeded. And this is a true positive, that is 147 startups were correctly predicted as successful. And these are the top predictors for random forest model with original and engineered features. And in innovative support index was the highest, followed by innovation funding interaction, total support, and a few others. So this highlighted the key factors driving the startup success for random forest. So finally, I compared all the model performance, and as we can see, that logistic regression with the original features has the highest accuracy of 97.1%, and ROCOC of 0.99. We can say that feature engineering did not significantly improve the result, which indicated that original features already captured the key patterns. And so I used this model for deploying in Streamlit to enable real-time predictors for startup success. And this was just a graph for ROC curve for both logistic regression and then random forest. And as we can see that logistic regression shows near perfect class separation than random forest. So this is a Streamlit application which predicts the student startup success based on team and other project details. So user basically inputs the team size, experience, funding, support, and they get instant success probability. And this built with Python and ML, and it is publicly available on Streamlit Cloud. And I've also attached the link at the top. So in this project, there were some model limitations like logistic regression might miss nonlinear relationship, and random forest could overfit the small data set, and there were no external market or regulatory factors included. So in future, I plan to add more features like market trends and founder backgrounds, and also test advanced models like XGBoots, etc. And I also plan to enhance the Streamlit app with charts, explanation, and batch prediction features. So, the key takeaways for this project was that the logistic regression provided the best balance of accuracy and interpretability. And we can say that funding, mentorship, and innovation were the strongest success predictors. And also, data driven models can help universities and incubators identify and support high potential student ventures. So, basically, this project demonstrated how machine learning can generate actionable insights for entrepreneur programs. Thank you for watching my presentation. Feel free to reach out for questions, feedback, or any collaboration. And I hope this analysis helps to contribute better decision making in student startup ecosystem. And also, I'll be attaching a demo for the Streamlit application at the end. This is the startup success prediction application where it is publicly available on Streamlit Community Cloud. And I'll just show you a quick demo on two scenarios, that is positive and negative. So let me first go with the positive scenario. and I'll just change the project domain to financial technology, increase the average team size to 4.28, innovation score to 0.65, and I'll retain the funding amount to be higher. And then I'll just say that the project received mentorship support and incubation support, and my market readiness level is around 4, and I also have a bit good business model score of 0.72, and let's see what the model predicts. So we can see that the startup is predicted to succeed with probability of 100%. The reason because I have increased the innovation score, business model score, and market readiness level, and also we can see that the funding amount is higher. Because these were the top predictors of the model, the model is likely to predict the startup as succeed. So let's try the other scenario where I decrease the average team experience, innovation score. I also decrease the business model score, and I'm not ready for the market readiness level. And I say that I didn't receive mentorship support. So let's see what the model predicts now. So yeah, as expected, the startup is predicted to not succeed with the probability of 0.43%. The reason, as we know, all the top predictors were reduced for this project. So feel free to test your scenarios and let me know in the comment section how you feel about this project. So thank you for watching.